Hi guys, I just thought we'd have a quick introduction before you watch this video. This is all you need to know about switch mode power packs, the little wall warts, the little power supplies we find for many devices to fix stuff. It was meant originally to be one video with 8 physical examples and some in-depth study into how the circuit works, the variations that we find, and an in-depth study into the feedback system, how to test if the feedback system is working if you have an unstable power supply or one with the incorrect output voltage. However, the video got rather long, so I decided to split it into 2. So this is part 1. We're going to look at 4 power supplies. We're going to look in depth at how the circuit actually works, and then look at the variations in the 4 power supplies we have and see if we can fix them. Part 2 will then continue with 4 more power supplies and the in-depth look into how the feedback part of the circuit works and how to test it. Okay guys, hope you are looking forward to watching this. Here we go with part 1. I'll see you all at the end. Hi guys, welcome to another Learn Electronics Repair video. I have here a handful of power supplies, wall warts, whatever you like to call these things, that are not working. They're mainly 5 volt and some 12 volt ones, and they either don't give any output or they give a low voltage output or that sort of thing. So I thought it might be interesting to have a look at these just to see what generally goes wrong with these sort of power supplies. Have a look at the circuit, let's see how similar all these are, and let's see if we can actually fix a few of them as well while we're doing that. Yeah, so the first thing we have to do is get inside them. I mean, this one seems fairly easy because there's some screws on it, but that's quite unusual. Most of these don't have. So we can get into this one, and now let me show you how to get into other ones as well. We'll start with the easy one then. Let's have a look what's inside this. Just remove these 2 screws, and with a bit of luck it will just open up then. It's quite unusual to find one of these screwed together. This one's 12 volts, 3.5 amps. Could be a bit useful, I guess, for something. So open it up. There we go. And then, does it come apart? Well, interestingly, although the 2 screws come out of it, it doesn't actually come apart. Now, there's a couple of techniques with opening these things up, so I'll show you the first one, and then if that doesn't work on any of them, we'll try the second method, yeah? So I'll just get some tools, and then let's see if we can get inside this. This method works quite well with these. So basically taking a flat blade screwdriver, hold it near one corner and then hit it with a hammer, or in my case a large adjustable spanner, because I was using the hammer at home and I forgot to put it back in my tool bag. So quite often this will do it, yeah, just one blow on the corner and then it comes apart. So that one's opened. There's quite a bit of power supply in that actually. So we have that one, we can have a look. Let's see if we can get inside any of the other ones by the same technique. So this is another one of the flat ones. Again, we'll try the same method. So we get into one corner and we'll just hit it with the hammer and see whether or not it does it. Didn't go on the first attempt. Let's have another go. So actually no, it did go, it split it, it did it. So I'm going in roughly where the mains power connector is. So that one's apart. Again, there's quite a bit inside this one. So that's the second one we can look at. This is a 5 volt 2 amp. So we can see what's going on with that one. Let's have a look at the others. So again, we'll try the technique. We'll come in by this corner and see if we can get it to do the same. This one's quite solid. I'll just try a little bit further in. Now this one doesn't want to give it up that way. Let's try the other end, sort of near where the power comes out of it. So this, yeah, that one's going, yeah. So the same technique works, just took a few times to find the correct place to go in at it. Can we split it? No, so let's just go for the other side as well. This one is not easily wanting to give it up. Let's come back to that one. See if we find another one we can get in. Let's try this one. We'll come back to that one though. You know, we won't give up so easily. Let's try this one. So this one's a 5-volt 1 amp. Let's see if we can get it in somewhere here. Not easily. Again, let's go into here where the cable comes out. No. Try this end. So you see those flat ones, the square ones, are obviously easier to get into than these things. So we go in this end of it. No, that one doesn't want to give it up easily either. That's 2 successes, 2 fails. Let's try this one. Can we get into here? Not easily again. Go from the other side. No, so this type obviously don't really like it being opened up this way. Ah, that got it. Yep, that one got it. So that one we're getting there, yeah, we're getting there with this one. Let's go the same place on the other side. Of course, you might hit the circuit board, just, you know, just have to take a chance. So we're into that one, okay, so that one's open. So that's 3 succeeded. Quite therapeutic this, isn't it, guys, don't you think? Quite therapeutic. Well, that seemed to work well, going roughly where the output cable is. So just untangle this one. There we go. Let's try it. Getting that seam. So I'm basically hitting it where the seam is. Well, this one just broke. Try it here. Now this one's kind of breaking rather than going, but it's going to give it up, I think. I think we can say, yeah. We're inside this one. Ah, okay, I think that might have something to do with the fault on this one. What do you think, guys? That might be related to the fault on this one. Okay. 2 more. 2 more. A bit grubby, this one. 5-volt 4 amp. Again, we'll try down in this corner, see if we can get this one to open. Yeah, that one's going to go, I think. I wouldn't suggest you try this after you've just tried powering it up, by the way. There might be some charge in the capacitors, yeah, so I wouldn't suggest you open one of these up after you've just tried it and it was completely dead. Okay, so I have to go onto this side of it. Okay, yeah, so that one's opened. Last one. A few broken bits, but we can always stick this back together with the epoxy resin. 5-volt 2 amp. Let's try it. Might be an idea to hold this in a vise, by the way. No, that one's gone quite well. Yeah, that opened easily. So we're just down to these two that didn't easily want to come apart. I can try again, and if it doesn't work, then we'll have to use the Dremel on these ones. That's the only other way, really, I think. Yeah, this one is obviously very well stuck together. And I think we can say the same with this one as well. Not very easy, this one, even just getting it flat to hit it. No. So we have two that we have to use the Dremel. Okay, so the technique here then is just go down the seam with the Dremel. And the technique is not to go too fast with the disc and not to cut too deep. It's probably better to hold it in a vise. I have one, but I can't easily get it into the shop to record. So we have to go at it this way. And that might do it now. So if we go back to the original technique with the screwdriver, this might now actually just open up for us. Let's have a go. Yeah, that's now decided to do it. So we get it open. Still being a bit awkward. Again, you can see the end of the PCB there. Okay. We're open, hopefully without damaging anything. So that one's open. And we have the last one, this one. So again, this has to use the Dremel. And we'll use the same technique. But this won't cause a problem when you want to put it back together if you fix it. A bit of Araldite, 2-part epoxy resin, whatever brand you like. We'll stick it back together just fine. So this one is still proving difficult. This is proving the toughest of all of them. Right, it's going. Let's see if we can. Yeah, we've got it. Okay. The PCB is vertical in this one. Actually, I can see the PCB. Obviously, did not want to come apart. That's interesting. Huh. Yeah, there's that little metal pads on here that it presses against that makes a contact. Yeah, I wonder if that was just what was wrong with it, bad contact. Okay, we're in there, so let's clean up the mess and now let's have a look, see what we've got. Just a quick word of caution before we look to repair any of these. These power supplies will have high voltage capacitors on the input. We can see them on these quite clearly. So this one is marked 400 volts. This one is a bit more difficult to see, but these will be 400 volts, and so on. There's another one. In this case, the capacitor is hidden actually down under there, but it is still there. So all these power supplies will have high voltage capacitors on the main side. Now, this capacitor during operation charges up to about 320 volts DC. And normally, because the power supply is running, when you switch off, the power supply will discharge the capacitor. But in some instances, when the power supply is dead, depending on the nature of fault, you might have a situation where the capacitor charges up to 320 volts DC, but does not discharge. And in this case, it can be hazardous. So if you touch the circuit in this area, anywhere around this capacitor, you can get a shock, and quite a nasty one from it. So you need to understand that if you're going to repair power supplies. And you need to check always after it's being plugged in and then disconnected from the mains if there's any charge in this capacitor. It's fairly obvious, I think, to most people that you're not going to be touching around here when the thing is powered up and switched on and connected to the mains. If that isn't obvious, don't start repairing power supplies until it is obvious, yeah? But it's less obvious this may contain a high voltage charge. So it's something you need to be aware of, and you'll see me mention this several times during this video. Now we've opened them up, we have 4 very basic ones, or fairly basic, and we have 4 that seem to be rather more complex. This is one of the basic ones with something broken, and we have another one here. So let's look at these 4 first, and then let's take a look at the other ones. So this is very typical of a simple power supply, and I think we should zoom down on this and have a look to see what we have. This is about as basic a supply as you can get, really. We have one IC which will be driving the switch mode power supply. We can have a look. Yeah, a part number on each. Can we read it? SP5618P, okay, or BP. I think it's 5618P. So that's the chip that's driving the transformer. There's no MOSFET switching the transformer. The MOSFET will be built into this chip itself. This is the high voltage side. If you look underneath it, you can see there's effectively a big gap across here in the middle. So this is the high voltage side, which has effectively hot ground. This, I suspect, is a bridge rectifier down under here. Yeah, it's got plus and minus. So the AC comes into here, plus and minus comes out via a couple of resistors, and it looks like it goes to this capacitor here. So that'll be the main capacitor. Yes, 400 volts. The 202 on it. Yeah, there's 2 400 volt capacitors on these. There's 2 main capacitors. A switching IC driving the primary of this, and then this is the secondary. Now this one doesn't appear to have an Opto-Isolator. So normally there's an Opto-Isolator between the low voltage side and the high voltage side, giving feedback, and this does not appear to have one. It could be that there's another secondary on this side of the circuit, so it's on the main transformer, but another secondary with a diode and capacitor, which effectively is what is being monitored. So rather than monitoring the output over here, it's monitoring another output secondary over here. That's possible, because it must have some sort of feedback. Let's plug this one in and have a look to see what's wrong with it. I can see what the problem is with this one straight away. These 2 capacitors, you see they bulged on the top, so they're bad capacitors, and they will need changing. They may well be all that's stopping this from working. Let's just put the lid back on this, and let's just plug it in, and let's see what it's actually doing. Do we have any output voltage? I'll just put a bit of tape around it just to hold it together while I plug it in. I'll see what we have coming out of it. So this is the output end, so we'll just plug it in, and let's have a look to see what the problem is with this one. Meter wants a bit of a clean. I'll do it in a moment. Volts. And this is the output. What's this one doing? Yeah, it's giving a little bit. It's like it's trying to start, yeah. I suspect, I'll just switch it off while I unplug it. I suspect with this one, if we replace those output capacitors, it'll probably work. Okay, I've cleaned the meter. So we'll just check there's no charge in the main capacitors, or capacitor, to make sure it's safe. And now let's replace those output capacitors on this one. So we'll just check it's okay. To do that, I need to measure the voltage across these large capacitors. So I'll just gently open it up so I can get to the rear of the capacitor. And let's see if there's any charge in them. So we'll just go on this one, negative. Yeah, about 22 volts, and then have it the other way around. And it's dropping away. So about 20 odd volts in that one. And we can just go to the other one, which is over here. Okay, let's have a look. That's there, yeah, so it's over here, it's this one. Let's have a look, see if there's any voltage in this one. Yeah, about 20 volts. They're fairly safe. I can always discharge them using the resistor. This is a 3.3k 5 watt, I think, resistor. Just move the legs a little bit closer together, and I can just connect across the actual capacitors. One here, one here, and we can check again, but I'm sure that it will be discharged now. Let's have a quick look. One here, yeah, 1.7 volts, and the other one here, 2.4. Okay, so let's remove these obviously failed capacitors here, the bulged ones, and then let's have a look to see if this one actually works. These should be fairly easy to remove, to be honest. Just yeah, probably have to add a bit of leaded solder. I could use a vacuum desoldering tool, but let's just do it the other way, with the basic tools. So we'll just get some solder on these. Okay, that's the other leg. Okay, and then we can just effectively rock it backwards and forwards, and it should just come out. And this one's got a bit of glue on it, so that might hold it in place a bit. Now it's coming. It's coming. So we just actually pull it out. Wait for the moment for the solder to just solidify. Go to the other end, you see. Wait a moment for it to solidify. Back to this end, and this is coming. Yeah, one end's out already. And that's the other end out. So we can see the negative. Oh, it's marked in black anyway, so that's that one. That's the green one nearest the end, and let's have a look at the other one. So the other one is here. Okay, try and keep it in shot for you guys. I've moved everything around a little bit, so, hopefully to improve the videos actually, but we'll see. Let me know what you think of the sound. I've got a new, well, I say new, I found a used microphone at the flea market yesterday. But they had quite good reviews. I bought it and it's working. And while we've talked about that, we have the other capacitor out. That's the other one. So I'll just use a bit of solder braid now. Let's get the thing clean, and now let's have a look at these capacitors. So it's out, that's out. Just get the holes. Yep, those are cleaned. Do the same with the other one. Where was it? It was here. There's this one. Just get to it. Okay. Yep, that's clean. Well, I think it's clean. Let's have a look at the other one under. A bit fiddly to get it balanced into work on it. Just try again. I'm sure this is where it is. It's down in amongst these. Yep, let's cut the end off that and let's stop messing about, eh? Stop messing about with this, the end off that, right. It's coming from this angle. There we go. Yep. Yep, okay. So that's ready to have new capacitors. What are these? So we have glue off it. Can't easily read it. But if you guys can read it. 105 degrees. There's a value, it's kind of underneath the glue. So we have 680 microfarads, 10 volts, 10 volts, 680 microfarad. And this one the same. They're both the same. Okay. Is it worth checking them on the ESR meter? Yeah, why not? We can have a quick look at these, see if we can add them to our Hall of Fame. So I think the highest I ever read on an ESR was about 60 ohms, apart from one that's actually read open circuit. So let's have a look. See how bad these are. Okay. We can add that one to the Hall of Fame, guys. Open circuit. Make sure the meter's working. Yeah. Just zero this. 1 moment. Yeah, pretty much zero anyway. Okay. How's it reading? Open. Open circuit. We can add that to the Hall of Fame. Hall of Infamy. Yeah, the Hall of Infamy. What's this one really? Open. And this is on the 100 ohms range. Yeah. They're about as bad as you can get. Let's stick some more in it. Let's replace them. I didn't have any 68010, but I've got some 1016s. These are good enough. These are low ESR capacitors. Let's just see how these read in comparison. So I'll just put it the right way round. Yeah, let's have a look at this one. Yeah. So you can see that those other ones were definitely bad. Yeah. I'm interested now. Are you guys interested? Do these actually read any capacitance, considering the ESR was so high? I mean, what I'm wondering is, would a capacitance meter or your multimeter on capacitance range actually tell you those are bad, apart from the fact you can visibly see they're bad? So this is one of the good ones, reading 1000. Yeah, nicely. This is one of the bad ones that we've just taken out. What's it read on capacitance? Well, it reads 0, yeah, I'm honest, it reads 0, so the capacitance meter would have told us that was bad. Found the other one, so I'll have this one as well. So, how does this one read? Yeah, they just open circuit completely. Okay, let's replace those, and then let's see if this power supply works. Okay, I've replaced those two capacitors. So let's again just try this to see if it actually is working now. So we'll just put the lid on. We'll use a bit of tape again just to hold this in place. That's the wrong lid. Let's try the right lid. Yeah, there we go, that's the right one. So we can just hold the top on for now. Okay. And once again, I'll just put the light bulb on the current limiter now as well, just in case nothing happened, didn't light up. Is this working? Yeah, so that one's working, that was repaired. So in that case, it was just the fact that the capacitors on the output were gone. Just before we move on to the next one, let's have a quick look at the data sheet for this chip. And let's see if we can figure out how the feedback circuit works, since I cannot see an Opto-Isolator. Okay, so I found the data sheet, but it's all encrypted in Chinese. So I don't actually know how this regulates. We have a block diagram. There's a voltage reference here, and I imagine this is effectively the input that's monitoring the output voltage. So my first guess, without trying to figure it out, is that the chip itself maybe has another secondary on this side of the transformer. I mean, I can see, and I'm sure you can see, there are effectively 4 pins on the primary of the transformer. So we can have a quick look, but this might not tell us a great deal, because normally there would be a secondary here that actually powers the controller chip. But we can have a quick look. So we have the voltmeter. Let's just check there's no high voltage in the capacitors, that they are discharged. Yeah, about 12 volts. So nothing dangerous in there. Yeah, about 6 volts in that one. I can just short this out because there's no high voltage in it. We can just get rid of any voltage that was in those. Yeah, it's gone now. So it looks like there's one. This is the high voltage end of the capacitor, I would say. Yeah, this is the positive end. So that's coming to here. So I'm guessing this is the primary winding. Go to resistance range so we can see anything useful. Yeah, there's a winding there. This end goes to the positive of the thing, and the other end goes to the chip. Yeah, so that's effectively that. And then there's another winding here. Let's have a look. And it's not connected to it. So there's another winding here, and that one, I suspect, is possibly powering the chip, and also it's being monitored as a feedback. That's kind of my best guess. Obviously, it's not really monitoring the output voltage as such, but I can't think of any other way that's working. Okay, so that's one is fixed. I suppose I better draw that on a bit of paper because it's a little bit complicated what I'm suggesting. And we can put the lid on this one. Let's have a look at how these power supplies actually work. So we have coming in the main supply, live and neutral, 220 volts, 110 volts, 240 volts depending on where you are. But this is AC. And the first thing we need to do is convert this to DC. So we have a circuit called a bridge rectifier, and I'll just draw that now. So the bridge rectifier has 4 diodes inside it, either made up of 4 individual diodes or one encapsulated unit called a bridge rectifier. So we have, let's draw this one as well. Okay, we have another diode over here. The 2 cathodes connected together, and this is the positive supply coming out, and then we have 2 diodes going the other way. So we have 2 diodes like this, one here and one here. And again, these are connected together with the 2 anodes connected together, 2 cathodes, 2 anodes. And this is our negative supply, DC. So the way this basically works, and I might as well colour with all the diodes because they're all the same, so let's make them all look the same. Don't want to confuse anybody with any silly little things. So basically, this is AC, so alternately one end is positive with respect to the other one. Yeah, alternately 50 times a second, 60 times a second, depending on the frequency of your mains, 50 Hertz, 60 Hertz. Okay. So when we're on one off cycle, this end is positive with respect to this end, and the current flows like this. The diode passes current one way, positive on the anode to the cathode, so the current flows through here, up here, and down here into our power supply circuit. And the current returning, because it has to complete the circuit, comes up through here, And now you might think it can go both ways when it gets to here, but it can't, because this end of this diode is more positive than this end, okay? Because of the positive is here, and this is more negative. So the current has to flow this way. This end of the diode is more negative than this end. Yeah, this end of the diode is more positive than this end. So the only one that's forward biased is this one. Yeah, more negative is like saying more positive at the other end. So the current flows down there. It flows through here to here. So what you get here coming out, effectively, if we call this ground, and I haven't put an earth symbol, and I'll tell you why in a minute. If we call this ground, then if we measure from a meter to here, this will be more positive. It's the positive half cycle. And what we get here is a positive half cycle. Yeah. What happens when we go to the negative half cycle? Well, at this point, let me find a different coloured pen. Okay, a blue one. So at this point now, this end is more positive, and this end is more negative with respect to each other. So this being the more positive, the current flows this way, yeah, the opposite way, until it gets to here. Now this diode is reverse biased. The diode always passes current in the direction of the arrow, positive to negative. So the current flows through here to here. So again, when this end is more positive, the positive half cycle comes to here, okay? The current has to complete the circuit, so it flows back through the load to here, yeah? Let's draw it this side. Back to here. Now we have the same situation. Which diode is forward biased? Well, the negative is over here. So this point is more positive than this point. So the current flows that way. It can't flow this way because this end of the diode is more positive than this end. It's reverse biased. So the current can only flow that way, and it completes the circuit back to life. So that's how it works, and your positive is still here. At this point, the current is still going the same direction. At this point, it's still going the same direction. On the AC side, it's reversing its AC. Yeah? You can see that. Current here is reversing, current here is reversing, current here is always flowing this way, and current here is always flowing that way. So, if you were to look at this with an oscilloscope, what you'd see is you now get the half cycle coming through again, so you get another positive half cycle. You get the next half cycle, and the next half cycle. So you get only the half cycles, only the positive ones coming here. This is always positive, okay? In actual fact, what you're doing, if you imagine, or even look at it, you're taking the negative half cycle from here and turning it upside down, yeah? Where the negative half cycle goes. So the first thing is, this is always positive. The second thing is, think about it, the frequency now is twice this frequency. Yeah? Because you're getting two half cycles in the space of one cycle. So the frequency here is 100 Hertz to 120 Hertz. Well, not two, it's either 100 or 120 Hertz, depending on your mains frequency. So that's how the first part of the circuit works. This hot ground. This is not safety earth, this point here. If you look at it, this point here on one half cycle is connected to the neutral via this diode. Yeah? And then the other half cycle, this point here is actually connected to the live via this diode here. Yeah? So that is why this is not safety ground. This is hot ground. You cannot connect anything earthed to here. If you connect an oscilloscope or a USB device to here, you're effectively connecting the ground of your computer, your oscilloscope, or whatever else it is, to live and neutral alternately, and it will not like it. Yeah, you'll probably
blow the bridge rectifier, you'll probably damage your test equipment. If you connect yourself to here, you're connecting yourself alternately to live and neutral. Yeah, 100 times a second. You won't like that either, yeah, believe me, you will not like it. So don't connect anything to here unless it's safe to do so. And what I mean by safe to do so is some isolated equipment like a multimeter that's designed to handle high voltages, that's safe to work on high voltages. Your meter probes, that's what you should be connecting to there. So you can see now we have DC here, but it's pulsed DC, it's not a steady DC. We want a nice, smooth, constant DC. So we connect across here an electrolytic capacitor. Maybe one, maybe two in parallel, depending on the design of the power supply. In some power supplies they actually have two of them connected in series, but not on these small ones, so we won't worry about it for now. ATX power supplies you often find two of them in series because it's a different design, but that's not really in the scope of this video. This is small power supplies, so there's normally one, sometimes two in parallel. The capacitor charges up to the peak voltage here, which on a 220 volt AC supply is about 320 volts, the peak voltage. So this capacitor, this is the positive end, will have here about plus 320 volts with reference to there. So that's what you would measure on your test meter if this circuit is working and the capacitors are fully charged. Now, we've got a DC voltage, which is what we wanted, but I suspect we didn't want 320 volts. We wanted something like 5 or 12 volts. Yeah, that's the whole point of this. So we need to reduce that voltage. And this is the way we do it. We have a controller chip, which is called a pulse width modulator. But this pulse width modulator also contains a MOSFET in the same chip that drives the power supply. The power supply itself consists of a transformer, like so, and then this is internal in the chip, yeah? Inside the chip we have a MOSFET, and that connects to hot ground. Okay, there's our MOSFET. And this connects into a pulse width modulator, PWM. I'll explain in a minute what a pulse width modulator actually is and how it works. Let's look at how it works, yeah? What the pulse width modulator does is it switches this transistor on and off very rapidly, over and over again. This transistor is a transistor, MOSFET, whichever you want to call it, yeah? It's a MOSFET. It's a type of transistor. Okay, enough about that. Right. So the pulse width modulator switches this on and off very rapidly. And by very rapidly, I mean into the hundreds of thousands or even millions of times a second. So it's quite common for these power supplies to run at 500 kilohertz, 800 kilohertz, something like that. It could be a bit lower, it could be a bit higher, but it's somewhere normally in the high hundreds of kilohertz that this is switching on and off. When the switch is on, current flows into the inductor, and that current would flow through our MOSFET to ground. The inductor has a very low resistance, so effectively this is a short circuit. But because this is an inductor, it has inductance, it doesn't start to pass current straight away. It has an effect of limiting the current that flows through. And what happens to the current is it charges up the magnetic field in the coil. So the current is being used to charge the magnetic field. Once this is fully magnetized, the current can then flow straight through, and effectively this is then like a short circuit. So before that can happen, this pulse width modulator turns this transistor back off again. I say transistor, MOSFET. Okay. It turns back off again. What happens now is the magnetic field collapses. Yeah. So the magnetic field collapses and it induces, turns itself, if you like. When it was charging this up, it was turning electricity, current, into magnetism. When it collapses, it converts magnetism back into electricity. So the current continues to flow through while it collapses, yeah? And that's what's happening, so it's charging and discharging it there. On the other side of this, because it's a transformer, not just an inductor, is a secondary coil. And this feeds our output. Well, before we just mention that, let's just talk about this inductor a little bit more so you can visualize how it's working, yeah? Let's find a bit of space on here. And then let's talk about the pulse width modulator as well. I said I would describe how that works. So first of all, the inductor. How the inductor circuit is working. Best way to imagine this is like a water wheel. Okay. So imagine we have a pump. And this is a closed circuit. So effectively, it has a reservoir of water. It pumps the water out of here, which flows through the pipes and returns here, yeah? That's what we have. So, this pump is connected. See if we can draw it well, yeah? Sort of, okay. This pump is connecting to a water wheel. This effectively is our inductor, yeah? That's the water wheel. And I'll draw as well, we also have a narrow section of pipe here. Comes to here. And this then returns back to our pump. Did I draw it right? No, I didn't draw it right. How about that? It's not closed there. Okay, it's not closed there. So, think how this works. We start the pump. The water wheel is static. It's not moving. Okay, it's not moving. So the water comes down here, but the blades of the water wheel are not moving. So water comes into here and starts to put pressure on this pump, this blade, yeah? Some of the water actually flows down this way through this narrow section of pipe, which restricts the amount that can flow. So a small amount of water comes down here, flows down here, and back into our pump. We have a circuit of water, yeah? But the water gradually fills up into this water wheel, so it puts more pressure on the wheel. The wheel has inertia, it's quite heavy. But under the force of water, it starts to move. So this starts to rotate. Yeah? At this point, the positive pressure is here. Yeah? This is the pump, the pressure of the pump. The pressure at the other end is lower. Less positive, more negative, yeah? Than here. And that's because we have a restricted pipe. There's less water coming through here. It's restricting it. And this isn't allowing the water to come through yet. But this starts to rotate. And as it starts to rotate, more water starts to come through the water wheel. And it starts to spin. And gradually it speeds up. And once it speeds up, effectively all the water can now flow through the water wheel. Yeah, it's whizzing around. It's not restricting the amount of water flowing anymore. So we now have a lot of water flowing through our water wheel, down through our pipe, the thick pipe, it's not restricted, and back into our pump. Huh? That's what the inductor's doing. So this is the water wheel, it's static. At first, very little water, very little current can flow through this. And the current in here has been used to charge the magnetism. In here, the current is effectively filling the water wheel with water and exerting pressure to start it moving. They both have inertia. This has physical inertia. This has electrical inertia.
but the analogy's good, yeah? Now, look what happens when we switch the pump off. Yeah? So you have your PWM, if you like, your pulse width modulator, controlling the pump. It switches it on. This gets spinning. Once this gets up towards full speed and the current is high, flowing, it stops. Okay, so the pump now stops. There's no more water coming in here. But what's the water wheel going to do? Well, it's big and heavy. It can't just stop. It slows down because the pressure is gone, but it's still spinning as it gradually slows down to a halt. Yeah. So this keeps on rotating the same way. Yeah. Now look what we have. The highest pressure of water is on the water coming out of the water wheel. Yeah. The high pressure is now on this side of it. The pump isn't running, so the low pressure is this side of it. So this end suddenly becomes positive with respect to this end, which is now negative. Yeah, and as the water wheel slows down, the pressure here will drop and drop and drop until effectively the water wheel stops. Yeah, but if we switch this back on, the water flow, before it stops, it'll speed up again, and you'll get this situation where either the pump is pumping and this end is a high pressure, the positive, or the pump isn't pumping and this is still spinning and this end is a high pressure, the positive. Yeah? So the positive end is reversing. That's what's happening with our inductor. And I hope you can see from that, picture it in your mind, picture it what this is doing. And that's what's happening. So the pulse width modulator is turning this on and off at a sufficient rate that it controls the current flowing down through this inductor. And by doing so, that controls the voltage which is induced into the other winding. So when the magnetic field builds up, the magnetic field effectively goes through the turns of this winding and induces a bit of electricity. When the magnetic field collapses, it induces voltage into both of them. It's collapsing. The magnetic field is passing through both coils, yeah? And so we get an output voltage. And the output voltage is actually generated when the field collapses, rather than when it's being charged. Or almost all of it does. So on the output then, we now have pulses of power. We put a diode in here, we activate a diode, and that effectively just lets the positive pulses through. It will block any negative, because there's going to be some negative off as well. Only the positive off come through. And we have the same thing, we have a capacitor, or some capacitors in parallel, from here to here, and this is our voltage out. Yeah, and this end of the winding now is connected to safety ground. There's no connection from this ground to this ground. This is safe. This is isolated from the mains. We have what they call galvanic isolation. Galvanic refers to the magnetism. Yeah, that's what we have. Now, the amount of current flowing through here and the amount of current induced into here, therefore the amount of voltage generated, will depend on the width of the pulses. So if we have a situation where the pulses that are turning this on and off are equal size, in other words what's called a duty cycle is 50%, yeah, we'll get a given voltage. The wider the pulse becomes on compared to the off, the more power will come through. The bigger the magnetic field. When it collapses, the more current it induces into here, the more voltage. And the narrower we make them, yeah, the less magnetism here, the less power, the less voltage induced. You'll notice, by the way, or you should do, that the frequency is the same. The frequency doesn't change. It's just the width of the pulse that's changing. So how does a pulse width modulator actually do that? How does it generate these narrow or wide pulses? Yeah. And this is analog circuitry. This is not a microcontroller with a timer that counts up to, like, for example, 50, switches it on, counts to 100 and switches it off. And if you count to 60 or 70, you get a wider pulse. If you count to 30 or 20, you get a narrow pulse. It's not digital, this is analog. So let me tell you how it actually works, the pulse width modulator. And in the old days, this was all separate circuitry. Now it's inside this chip. So the way it works is, we have a circuit which is called an operational amplifier. An operational amplifier has two inputs, plus and minus, okay? When the plus input is higher than the minus, effectively it's turned on, and the output goes up to the supply voltage. Let's say the supply voltage is, I don't know, 5 volts, yeah? If this input is higher than this one, the output is 5 volts, yeah? If this input is lower than this one, the output is 0. And when I say higher and lower, we're talking by millivolts or even microvolts, yeah? So the way this works is this. On this input, we have a reference voltage, okay? And on this input, we have a sawtooth wave like this. It's an oscillator, okay? Generating this sawtooth. So the voltage ramps up, then suddenly goes back to 0. Ramps up and suddenly goes back to 0. Now, imagine, for example, the reference voltage is 2.5 volts. Yeah? And this reference voltage is internally generated in here. So in here, we have a voltage reference generator, and we have a sawtooth generator. Okay, now, let's look at our sawtooth wave. Okay. If our reference voltage is here, 2.5 volts, yeah? When the sawtooth wave goes above 2.5 volts, so this is higher than this one, the output of this will turn on, and it will go to 5 volts. So, if we look at our output, this is 0 volts, 5 volts, yeah? At this point here, the output will turn on, yeah, to 5 volts. And it will stay on until the voltage on here becomes less than the reference, which is when the waveform comes back down. So that will happen. And then when we start the next cycle, at the point again, there, and we'll draw the last one there, at this point, the output will turn on and stay on until this comes back down. And you can see, on the output of this op amp, we get pulses. Yeah? And the pulses are at the same frequency as the sawtooth wave, and the width is set by whatever it is on the reference. So imagine the reference voltage is lower, say it's 2 volts. Yeah? So your reference is now, let's do it in a different colour. Your reference is now here. Look at the output waveform. So now, at this point, the sawtooth is higher than the reference. So now, the output turns on here. Yeah? And it stays turned on until this goes back down. So we now get a wider pulse. Yeah? And it'll stay off until this reaches the reference voltage again, which is here. Yeah, it'll turn back on again. Yeah? And stay on until this comes down again, which is here. So you can see, by doing this, and we'll draw the last one in here. Yeah? We now get a wider pulse. You know, the pulses are now wider. For the simple reason, the reference voltage is lower. And I'm sure you can see that if the reference voltage up here was 3 volts, what would happen is, the output would turn on at that point, and we would and stay till this drops down, and we would now get a narrower pulse. Yeah, we'll draw our 3 volts across here. It's here somewhere. Yeah, that's pulse width modulation. So the frequency stays the same, the width of the pulse varies, and it's controlled by the reference voltage moving up or down. Okay. So if we connect this reference voltage in some way back to our output. If the output increases, the output increases, the reference increases, the pulses will become narrower. And if the output voltage decreases, the reference decreases and the pulses become wider. So this circuit can control the power supply to the point where you get just enough width of the pulse to get the correct voltage. And if you draw more current from here and the voltage drops, the reference voltage will drop and the pulses will get a bit wider, giving a bit more power to handle the load, and the voltage stays the same. And again, if the current drops, the pulses will become narrower and it gives a bit less drive to stop the voltage going up when there's less load. So that's how it works. So we need to add onto our circuit now this. So the reference and the oscillator effectively are internal. So in here you will have sometimes called feedback, sometimes called comp. You can have a few different names this pin. We'll have a pin on here, yeah? And internally, this effectively has a reference voltage on it. And by connecting this pin here to this, we can affect what the reference voltage is, okay? We can affect it. So what we have is normally a circuit like this. There's two things we need to do. One, we need to monitor the voltage here, and two, we need to maintain the isolation between the safe circuit and the hot ground. So we use an Opto-Isolator. So we'll put the Opto-Isolator here. And the Opto-Isolator has inside it an LED, and it has a photo transistor, which only has one emitter, since I didn't draw it right again. And the LED shines onto the photo transistor. And a photo transistor, effectively the base that controls the conduction, is photosensitive. So the more light you shine on, the more that transistor turns on. The less light you shine, the more it turns off. The output of this transistor, this end can go to hot ground. It's on the high voltage side of the circuit. And this end of it, not necessarily directly, maybe with resistors, goes to here. Yeah. So you can see now, as this lights up, the more it lights up, the more it connects this point to ground, and the more it pulls the voltage here down. Yeah. The less this lights up, the less this conducts, and the voltage here goes up. So that's how it's controlling it. And we're monitoring the voltage up here. And the way we normally do it is this. With a resistor to limit the current to the LED. Okay. Now the LED will light up when there's a voltage here, but we don't connect it directly to ground. We need the LED to turn on at a certain point, and to do this we use a voltage reference, or what's called a programmable Zener diode. It could just be a Zener diode, but it's normally this little chip, TL431. Okay. And inside here is what's called a programmable Zener diode, and this connects to safety ground. This is the safe side of the circuit, this is the hot ground side. We have another resistor coming down here, which I'll explain in one moment. Okay. And then we have, usually, two more resistors connecting to the reference pin, or the adjust pin. One goes to ground, and the other one goes to the point here. Right. These two resistors, the ratio of the two will set the point at which this Zener diode turns on. Okay? So depending on the value of the resistors here, we can make this Zener diode turn on at when a particular voltage is here. And we can choose what it's going to be. This resistor is to make sure that when the LED is off, this still has power. If you think about it, when this LED is off, yeah, this still needs to have power coming into this circuit, yeah, so we can set this to turn on to a certain point, and that's what it does. So when the voltage here reaches the required level, which depends on what voltage output we want, this LED now turns on. The zener effectively becomes short, but it maintains the voltage across it, whatever you've set it to, and the LED turns on. That signals back into here. It reduces the pulse width modulation, and when the voltage here drops, this turns back off again. So this circuit is a feedback circuit, and it maintains a certain amount of brightness on this LED that just maintains the right amount of feedback to give the right amount of voltage, and the voltage will depend on the value of these two resistors. So that's how the feedback circuit works. But this is not quite complete. We need one other thing. This chip needs power. It needs power to work. Yeah, it needs power. So this needs a power supply. Where's that going to come from? Well, initially, there's only one place the power can come from, and that's from here. Yeah, 320 volts. So usually, on these little chips, internally in here, is a high value resistor, which connects to here. When you first switch on, this power supply isn't running, this isn't switching. So this end of the coil is at the same voltage as this end, it's 320 volts. And this resistor passes a little bit of current to this pin, and from here we have a capacitor connecting to hot ground. So when we first switch on, the voltage here through this high value resistor charges this capacitor, and when the voltage in the capacitor reaches a certain point, this chip switches on. Let's say, for example, it reaches 15 volts to switch this on. This chip then starts running, driving the MOSFET with pulse width modulation, and starts driving the primary, which induces voltage into secondary. The power supply starts working. But this chip draws more power to run than this resistor can provide. So once the switch is on, the voltage in the capacitor starts to discharge. And the chip has something called hysteresis or hysteresis. And the way this is designed is that the chip will keep on running until it reaches a lower voltage, say 9 volts, and then it switches off. At this point, when the chip is switched off, this resistor can charge the capacitor again, and it switches back on. So this resistor can provide current to start the chip, but it can't provide enough current to keep the chip running. To keep the chip running, it needs another power supply. Because this is now running, it started to run, we can get the power from here. So we have on our transformer another secondary winding here, connected to hot ground. We have here a diode. Draw the diode the right way around, Richard. Yeah. We have a diode. Generally speaking, a resistor. And this comes back to here. So how this circuit is supposed to work? Initially, this resistor charges this capacitor, and it reaches 15 volts or wherever it is, depends on the chip, and it starts to run. Once it starts to run, it starts to drain this capacitor. But in the meantime, this is now generating power, and the power is induced into this secondary as well as the output. This diode rectifies the output, and it provides power back to here. And this circuit can keep this running. So once it starts running, it's this circuit which keeps the thing running. The idea of this is quite simple, yet it's quite elegant. If there's a problem, for example a short circuit on the output, it loads the power supply to such a point that the voltage induced into the windings is very low. So this can never start supplying. So after first switching on, maybe after half a second, depends on the value of the capacitor of the chip, it switches back off again. And depending on the chip, it'll either stay off, so when it switches off, it'll either keep this capacitor discharged or down at 9 volts so it can't start again, or it will switch off and stop drawing current, allowing this resistor to start it again at 15 volts. This is what causes this chirp, 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 chirp noise you sometimes see on the power supply or the output LED flashing. It's because the chip's starting, but something's preventing it from keeping on running. And normally there's something preventing it as a short circuit output. But there's another very common reason that it can't keep on running, and that's that this capacitor has failed. This is typically 10 microfarad, 35 volts, 25 volts, something like that. If the capacitor fails or goes very low capacitance, the resistor will charge it, it will start, but before the power supply can get running, it discharges the capacitor again, it struts back down. It can't hold enough charge to keep this running long enough to get this going. That's a very common failure. There's another variation on this which is so common, I really need to mention it. Some of the chips do not have this internal high value resistor. What they have is, from here, usually 2 or 3 high value resistors in series to here. And these might be like 1 meg, something like that, each. So in some cases the resistor isn't there, it's external, it takes a couple more components, so some of it built in. Again, the principle's the same. These resistors charge the capacitor. Once the voltage is high enough, this switches on, and if everything's okay, this power supply takes over. Most common failures. That capacitor fails, it won't start up, or it does this chirp, chirp, chirp. These resistors go open circuit, so it won't start at all, or we have the chirping problem. But normally they just won't start at all if that fails, to be honest. These resistors go high value, or this capacitor goes leaky, so it'll only switch on when it's hot, it'll only switch on when it's cold. It'll keep retrying chirp, 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 chirp for a couple of minutes, then kick in. All those sort of problems are caused by this, basically. It could be the chip, but normally caused by this. And one other common addition to this is we have, from here, the Zener diode running out of space to here. The Zener diode is to stop this capacitor overcharging, so that you can't get too much voltage supply into the chip. So that's about all the common things we have. All the things that can fail. Short circuit on the output is very common, either come with a lead, so effectively the wires are connecting together. Short circuit diode. Both of those will normally cause this chirp, 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 chirp thing. It won't start up. Could blow the MOSFET, depends, or the chip, depends on the power supply design. Short circuit here, MOSFET, would normally blow the fuse, so quite often there is a fuse in here. Yeah, or in the plug. You could also blow the diodes. Occasionally you get short circuit diodes. They will blow the fuse. These capacitors don't really tend to fail very often. So that's a basic, in-depth look at how a power supply works. I hope you kind of enjoyed that, yeah. All the common problems, what we're talking about them. This Opto-Isolator can fail, so the regulation doesn't work, and we get too much output voltage. Any of the resistors in this circuit could fail. The TL431 can fail or become unstable, so we get an unstable output voltage. This capacitor failing can also cause unstable output voltage quite commonly as well. Just mentioned that one. So the most likely things to fail, if you're looking at this in order, are this capacitor, these resistors, this diode, short circuit in the chip. Those are probably the most likely. And short circuit in the chip may well blow these diodes, it may well blow the fuse. Unstable TL431, yes, it's happened. It's not so common, but it does happen. And any of the other things. Any failure in this circuit, resistor or diode will stop this from switching on. You get the chirp, 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 chirp thing usually again. Some chips, they don't chirp. Sometimes once this goes to 15 volts and drops back to 9, it just stays switched off and it will not start again until you unplug the power and discharge this capacitor fully. Right, we've had a look at that. Let's have a quick look at our board, the one which we fixed with the capacitors. This is the capacitor on the startup circuit I was just mentioning. So this is that capacitor, which is that one, and this is a very common failure. The diode, this diode is this one, fairly common failure. Short normally, stops it from powering up. The chip, obviously we can see the chip. This one doesn't have high value resistors. This is a very low value resistor. So this will have this inside it. It doesn't have a separate MOSFET. This could be separate. Again, this is inside it. And what this one does not have is an Opto-Isolator. So how does this regulate? And what it does have, which I haven't mentioned, is this inductor here. This inductor is common, and normally it is in here. So the inductor, I didn't draw it very well. You have a diode, an inductor, and a capacitor. Like so, yeah, this is your out. This is your secondary. This inductor is to help the smoothing of the output, and sometimes they don't go open circuit. But what sometimes happens, because it's quite a heavy component, sometimes it breaks away from the circuit board, effectively goes open. So that's what basically goes wrong with these sort of power supplies. We'll have a look at one more thing on this, which is how the stabilization works. I've got a good idea, and then we can look at the data sheet, and then we can move on to something else. So our power supply, we know, does not have this, but it needs to stabilize the output. How does it do it? Well, there's only one way it can do it, and that is that the feedback is connected to here or to here. Yeah, the feedback is monitoring this voltage, or the AC here. The feedback effectively is monitoring from here to a resistor and probably another resistor to hot ground, and the feedback is there. So this must be monitoring something. It's got to be monitoring here, and I think the way it's working is that effectively it works on the ratio between this coil and this coil, the number of turns. So, for example, this might have 3 times as many turns as this one. So when this is 15 volts, this is 5 volts, and it's working that way. When this draws more current, it'll tend to load the power supply, so the voltage here will also go down a bit, and that's how I think it's doing it. It probably isn't as efficient as monitoring the voltage here, but for a small power supply with like 1 amp output or something, it's no doubt good enough. Let's have a look at the data sheet and see if that's the case. Here's the data sheet, which, as I said, was all in Chinese, but I do have effectively an example diagram, and we can pretty much see what we've been drawing out. It's kind of sideways, I can't really help you with that, but this is the main power. This is the large capacitor. This one has an inductor on here, which ours may or may not have, possibly does have. I'll show you in a minute. So this is where your power comes in. These are filters on the input, which ours doesn't have. This is the bridge rectifier I was showing you. So the positive output is here, and this is your hot ground. This shows a safety ground, but it's not, it's hot ground. So the 320 volts DC across this capacitor. This is the primary of the coil. This diode is to stop what's called back EMF, too much voltage getting into here when it switches off. This is, like I was showing you, like the big spike, the push of the water wheel once you turn it off is still pushing current through, so that's what this diode is to dissipate. This is the secondary I was talking about on the high voltage side that feeds the power back to the capacitor. And in actual fact, this has an external resistor by it looks of it. It could be internal. So when it starts up, this initially charges the capacitor. This is the high value resistor. I thought there wasn't on ours, but it must be on the other side of the board. This then starts running, switching through the coil, drain to source. This resistor is a current sensing resistor, by the way, which may or may not be present on ours. You can measure the voltage across this resistor, and this effectively tells you how much current is flowing through here. So it's a current sensor. This starts running and then induces voltage into this supply, which then back through this resistor charges the capacitor back up, so it keeps enough voltage on VDD to keep it running. That's what I've just described to you. Let's look at the feedback on this. It's called INV. There's two resistors, one connecting to hot ground and the other one, look, is connecting to this winding. So ours is in fact monitoring the voltage here rather than using an Opto-Isolator. On the secondary side, we just have the diodes, the coil I just showed you. Yes, ours does have two capacitors, I can show you those. And this is the output side. So basically this really looks much like our circuit. We can now just look again at this and we can see pretty much what we've identified. So this is the bridge rectifier, AC in, DC out, and this charges the large capacitor which is here. We can see that. This resistor is actually a low value resistor, 0.75 of an ohm, and this resistor effectively, if you look, one end is connected to the bridge rectifier AC in, and the other end here goes to one of the AC inputs. So the power mains coming in is actually coming via this resistor. This is just to limit the inrush current when you first switch on, because this capacitor is fully discharged. So we have that. There's a couple of low value resistors after the bridge rectifier, and then we go to another capacitor, which is this one. I would have thought those were actually inductors rather than resistors, but there we are. Look like the low value resistors. This is our chip in the middle here. You can see the various pins. There's a diode here. I haven't tracked it through, but this is probably the diode on the secondary. Yeah, this is one of the secondary, the one that's powering the power to this chip. That's what that one's for. And this is the capacitor I was talking about. That's this one. Yeah. The diode underneath this one will be this one. So that's what we have. Output, we have two capacitors and one inductor, which looks very much like that block diagram. It has a capacitor either side of the inductor, so there's another capacitor here. Two capacitors, one inductor, that's that. And there's the rectifier diode, as I mentioned before. So that's what we have. This one's working, so we can put this on one side now. Well, let's have a look at the next one and see how it differs from this circuit and what is wrong with that one, yeah? Okay, here's this one. We can see pretty much what's wrong with this. So let's see if we can fix it. First of all, I need to get the PCB out of the case. Let's see if we can do that. This is not being plugged in for about an hour or so, so I know there's no voltage in the capacitors. How are we going to get this out of here? Although we've got it open, it doesn't particularly want to come out. So if we can persuade this a little bit more. This has like an L-shaped PCB. I can see it from here actually. So this is not going to be particularly easy to get down into it. Let's try and grab hold of it with the pliers. Okay. See if it wants to come out that way. No. No.
I suspect this is actually looks like the PCB is actually glued into the case at the bottom. Oh, it's actually okay. Well, for the risk of damaging it further, we can't do anything with this if we can't actually get it out of the thing. Another reason I know there's no voltage in this, by the way, this is where the coil fits, and this is the filter on the input. So it's not possible for any voltage to get to the bulk capacitor because the coil's actually broken off. Oh, it's out. That took some work, guys. That took some effort. Okay, so this is very compact. We have, I think you can see, this is the input capacitors down here. This is the 400 volt 10 microfarad capacitor. We have a fuse on the input which clearly hasn't blown. That's then fitted to the main board which runs underneath, and then we have this little board up the side. This is the output diode, the rectifier. This is the output capacitors, and that's basically what we have. And what we know is wrong with this one is that this little coil is broken off here. So this should be like 2 inductors. Let me zoom down on it a little bit, you can see it. I've zoomed in then so we can see better what we have. So this is the output end of it effectively, the low voltage side, this side of this divide. Here we have the Opto-Isolator, which you can see there. So this is monitoring the voltage on this side and signaling back through the Opto-Isolator. This is the LED. This is the transistor side of the Opto-Isolator, and this is signaling back into the control, and here telling you when the output voltage is correct. This little PCB, which has the fuse, the bridge rectifier, and the first input capacitor on there, the bulk capacitor, and this should have the inductor on. So the inductor is here. You can see there's effectively 2 windings. This is not a transformer, it's a filter to filter out noise getting back into the mains wiring, and this is what's broken off, so this is why it's not working. Now we should be able to fit this back on, to be quite honest, but we could either, if we were really desperate, we could effectively bridge this out with 2 bits of wire and the thing would still work, but it would cause more mains interference, but it would give us an output voltage. So if we were stuck and we really needed this to be working, then we could do that. So to fix it, I need to get this PCB off. I can see that the PCB is there, so that's the edge of the PCB. And I'm guessing it'll probably just have 2 connections on, I would think. Yeah, you can sort of see them coming down here, yeah. So this is effectively the plus and minus. There's probably only those 2 connections on there, at a guess, and it's a matter where they're coming through. It looks like one of them might sort of come here somewhere. So let's see if we can maybe scrape a bit of this gunk off first, and now let's see if we can figure out how many connections there are and what we need to desolder. Not easy to get that off, so it's not easy to see where the connections are, but even so we've got to figure it out. I'm thinking, I mean, we can see where the line of it comes down here, so any connections have got to be here really. I can't see it being anywhere else unless it's on this side. They've got to be basically there. So I'm going to unsolder some of this and let's see if it will come loose. Let's see if it will come out. So we'll try this. We'll put some solder on. We'll get some solder braid and see if we can see anything obvious underneath here or here. Or here. Let's see what we can see. Well, let's clean the solder off those. So we get the solder from here as well. Okay.
Now let's see if anything's waggling around. I'm sorry if you couldn't quite see some of that. Let's see if anything... No, I don't see anything waggling around here when I'm moving this. Maybe it's over here. That seems a bit too far across to me, but let's have a look. I mean, this holds the metal bracket on. I can see that. That's a heatsink for the MOSFET. The MOSFET's down there, so there's a separate MOSFET. So, I can see one of them now. Yeah, I can see one. So, down there is a mounting pillar. So that's one of them, which appears to come into this area actually. Yeah, I think I figured it now with the magnifier. So this is one of them here. I'm guessing that that's one, and this is one, and they effectively been bent over to hold it down. So we need to clean the solder from here and lift this up by the loop socket to get this off. They obviously didn't make it easy, but I'm sure we can do it. Yeah, that's cleaned now. We need to get this cleaned enough to be able to lift it up without effectively damaging the PCB. So we get some more heat into that, and I'm guessing this is the other one. Yeah. Let's see if we can get underneath these. So this is one of them. Yeah, the pad's coming off. I thought it might do. Let's see if we can get some heat in and get it lifted at the same time. See if this will actually give us any better. No. Okay. The pad's come off with that one, but I don't think it actually goes anywhere. We can have a look. There's just these two things connected. We can. We'll have to bend this up now. We'll have to have a look to see if that was actually connecting to anything. So, unfortunately, that one didn't come off quite as well as we thought it might. Okay, let's see. It's bent straighter now. So that's two of them. Long nose pliers will probably help to finish that one off. Okay. And then the third one must be this one that's bent over here. Again, it's a matter of trying to lift it without damaging the board. Get something under the edge of it maybe, and try and get some heat in at the same time. Yeah, that one's come a lot better. That seemed more successful than that one, so get that one straight as well. Does our PCB come out now? There you go, guys, that's how it was. And it looks like, yeah, the one where the pad actually effectively came off, if you look the other side, there's nothing connected to there. So only, or is there? Yeah. If it goes anywhere else, I can't see where it is. Yeah, I've scraped away a bit of the hard silicone, and these two pins are actually connected together. And this one actually looks like it goes nowhere, but it actually goes to one side of this coil. So we need to clean off the 4 bits of solder where the inductor goes. fit the inductor back on and put this circuit board back on, it should work then actually, and that broken track on the other board really should have no effect. So let's clean this up. Let's use a bit of braid again, yeah, on this one. Let's use the braid so I can see where the 4 pins of the inductor actually go to. In fact, there's little bits of wire still stuck in them, I think. See if we can get them without adding any fresh solder, otherwise we'll just add a bit of solder. Usually as a case, a bit of leaded solder helps a lot. So let's get this one. Okay, this one. There we go. Now some desoldering braid. Okay, yeah, that's good. That was good. All good. All good. Yeah, all the pads are still on there. Okay, let's put the filter back on. Now, the wires on this basically are enamelled. So sometimes you'll find that you need to strip off the enamel. That's like the copper coloured stuff, if you like, the brown coloured stuff. But those are okay on that one. This side, yeah, they might be a bit too short to actually go through the board. So what we can do is we can actually just remove one winding from the coil. It won't have much of an effect on the performance of it. I mean, this one looks like it's probably going to reach. It's just this one. So this one looks like it's going to reach, but this one looks a little bit short. Let's see if we can get a bit more out of it. If it's long enough, we'll use it. Yeah, it looks like it probably is long enough actually. If you have to remove the enamel, the best way to do that is to use your soldering iron set at 400 degrees and effectively apply the soldering iron some solder, and at 400 degrees it'll actually burn away the enamel and you'll be able to connect it. So we need now to fit this back onto our little PCB. I've soldered this back in place, so we can just check it now. And you can see actually this is the output, and it comes through this coil here, and this comes this way, and then this goes to the large capacitor across here. So we can actually measure this. So this is effectively an output. Just get onto there with my meter probe, and that should come through to here. I just need to put the meter where you can see it. There we go. Oh, we'll go again. So from this output, and try and get in the shot, otherwise I have to do it a different way. We should have a connection to here. Yeah, almost 0 ohms, okay. And then the other one, which is here, this output, we should have a connection to here, the other side of the coil. Onto it. Yeah, almost 0 ohms. So that's now fixed back in place. I can put a little bit of glue to hold it, and then we can mount this back onto the main board, and hopefully this one will be fixed. I've put this little circuit board back on. I've bent the middle one over, but it doesn't need soldering because there's no actual electrical connection to there, as we can see on the other side of the board. So if we find a bit of solder, yep, get the solder before this falls back over. Let's see if we can, yeah. We'll attach our PCB back on. So that's back on. Now let's just put this back together enough to figure out if it's actually working. Again, I've just put enough tape to hold it together. I'll switch the power off. We'll get rid of this little cable tie on it, this zip tie. Does anybody know when these were invented, by the way? So I might just look it up. I was commenting on a previous video that I don't think we had them in the 70s when I was working on electronics as a hobby. Okay, so this doesn't have a connection on the end anyway, but it doesn't matter. We can have a look to see whether or not this is actually giving any voltage output.
Okay, so there's our wire. I have the current limiter switched in anyway. And this one is drawing a bit of power actually. Let's see if it's actually working. No, this one is still not happy. Oh, in fact the light bulb's just come on. So it didn't like that at all. I'll just actually move my camera over, you can actually see it under here. Yeah. Let's switch it on. Yeah. This has some sort of short on it. It was lit halfway up. I should have put the camera on it previously. And now this one has gone short, so it doesn't like something. So here's the power supply. It obviously didn't like that. I didn't have the camera pointing at the light bulb, but I was powering it with a 60 watt light bulb. It was always about half brightness initially, so it was drawing a fair bit of power. And I thought, oh, I'll just see if there's any output voltage. And in the meantime, the light bulb went to full brightness. So there's obviously some other problem on here. It's now short circuit, but prior to being short circuit, there was probably drawing a lot of power. Maybe there was a short circuit on the output, and I incorrectly made the assumption that the little coil that had broken off was the actual only problem. I mean, I can't see as I've knocked this off when I was using the screwdriver to break in, because I was the other side of this heatsink. There's no way I could have been hitting that. And besides, anyway, I came in from the other end as well. So that was obviously one fault with this, but he's had another fault. So let's have a look to see what's gone short circuit on our power supply now, and if we can still fix it. Okay, we have the meter on... we can go on continuity mode and let's see what we've got. So first of all, does this have any short circuit on the output? Why was it drawing quite a bit of current? Well, no, there's no short circuit on the output, so that isn't what was initially causing it to draw power. Let's have a look to see where the short is. So do we have a short on the mains coming in? No, we don't. And the meter is working. Do we have a short the other side of the bridge rectifier? The best place to test this is on the large capacitor. So let's see if we have a short across this. This is one end of the capacitor. No, there's no short there, but it's reading 550 ohms. So you read pretty much the same the other way. Yeah, a bit lower that way. Let's look at the rectifier diodes themselves. So we'll go to diode mode. Just missed it. There's a diode mode. Let's have a look at the bridge rectifier diodes themselves. So the meter's good. We have 4 individual diodes on here, so we can look at the first one, which is here. That means a diode junction. Go across. That means a diode junction, so there's no short there. The other 2 are down here. There is nothing that way. So this will be the negative, sorry, the positive side. Let's go to here. There's no short there. And then this should read open circuit this way. That's the negative. It should read open circuit the other way. Okay, this is not reading as you'd expect, because these diodes are actually reading both ways. And you wouldn't expect to find that. So look at that directly across the bridge rectifier. We read something across that way. Well, you'd expect to read across it one way, because there's 2 diodes in series, but you're reading both ways. So there's something not reading correctly there around that. I think what I'll do is I'll take this circuit board back off, and then let's have a look to see what we have.
there's our PCB off. We can see it quite clearly this side. So let's look at these diodes again. So we have AC coming in one end. Let's see if we just figure out which end's which. These two are the two cathodes. That must be the positive rail, and that must be the negative rail. So these will be connected together, and this is one of the AC sides. So this should conduct in this direction, yeah, in the direction of the arrow, if you like, towards the stripe. This one shouldn't. Yeah. This one should conduct in the other direction, yeah, and this one shouldn't. So those diodes are okay. The other AC rail will be this one, so these two will be connected together. This one should conduct this way, yeah, but not the other way. And this one should conduct positive to the anode, not the other way. So there's no problem with this bridge rectifier. Directly across the two AC terminals should be nothing. And from the positive to the negative, with the red to the cathode, so this is the positive rail, it should read nothing, should read open, yeah. The other way around, with the red to the anode, effectively the reverse of the way it is normally when it's running, this should read like two diodes in series. It does. So that's a good bridge rectifier. This is okay. So the problem is on here. Let's have a look where the power comes in. So this is where the power is coming in. What's that reading? See, that's reading quite low. Let's go the other way. That's reading quite low. There's something there. It's reading in both directions. There's something there which is effectively drawing. So not drawing current, it's reading what current's passing. This is the MOSFET. This is the most likely thing to have a problem. Let's look at the MOSFET. Well, that reads like a diode, and that sort of reads as well. Yeah, that's reading strange for a MOSFET. So what we need to do is take the MOSFET off and have a look to see if that in fact is faulty. I've unsoldered the MOSFET. What I did notice is I had a bad connection here. This joint wasn't soldered, or not soldered properly. So this is effectively where the negative end of the bridge rectifier comes in. It goes here, considered negative of the large capacitor, 10 microfarads, 400 volts. And it connects via a wire link across here. So this is a wire link. And that goes to a diode down here. Yeah, anode of this diode. And the other end of the diode disappears into this circuit somewhere. So I'm not quite sure exactly what it does. I haven't really looked at it, but that might be some possible reason why this failed. I'm not sure. Let's have a look at this MOSFET anyway. Because assuming it failed for some reason, it didn't fail straight away. It was drawing more power than you would expect, but not short, and then the light bulb on the limiter came on full, so it actually went short. Let's have a look at this. I'm guessing this is the gate, just because it usually is. So gate, drain, source. You'd expect to see a diode junction one way across this. And I'm seeing it both ways. So let's check this on our component analyzer. Let's have a look to see if this is actually any good. This is the DCA 55, a great little device. I bought this, I don't know, about 2014 I guess, and I've always been very pleased with it, never regretted buying it. It's done very good service over the years. So we can connect these on here in any order we like, and we can test it. And it's faulty, it's bad. assuming it is a MOSFET, and I would pretty much assume this is a MOSFET. Let's have a look under the microscope and let's see what type it is. Here is the MOSFET, part number K3, yeah, K3113B. So that's the actual device, and we can have a look to see what this is on the data sheet. And there it is. This appears to be a surface mount version compared with ours, so I may have to actually have a look for a different package. That's probably what all these letters here are referring to, but we know it's a MOSFET. So that's what's wrong with our power supply. The question is, why did it fail? Normally you'd expect something like this to fail if there's a short circuit on the output, but we've checked for that and there isn't a short on the output. It's possible it could fail if there's a shorted turn inside the transformer itself. That would put a load on it. Or it may have been in this case because I hadn't soldered one of the connections by the looks of it into one of these diodes. And this is quite an unusual design actually. If you look at this, there's no control chip. There's a transistor here, Q2. The MOSFET actually says IC1 as though it's an integrated circuit, but the data sheet, and I have found now the same package style as this one, and I found them for sale on AliExpress as well, and they all say this is a MOSFET. So we'll stick with that being a MOSFET. On the other side, there's a few transistors or MOSFETs, but there's no IC, there's no controller. So this must be a self-oscillating circuit. You find these in a lot of ATX power supplies on the standby rail. They often have this kind of self-oscillating circuit. This is stuck back here, and I'm guessing it's stuck back here for a reason. I mean, there's no reason why it has to have long legs and be glued back here. As I can see, apart from it must be for a reason. It's not by accident that that is fastened back there. It's marked as Q2, so we assume it's a transistor marked as Q. Without taking it off, it's all covered in this epoxy anyway, so I'm not sure if I can even easily read the part number. Well, I've managed to move it now, so let's have a look and see if we can actually see what this thing actually is. I have to say I'm a little bit at a loss as to why this is actually fastened back to the transformer like that on long legs. Okay, so this is a N, is it? H945P. Let's see if we can figure out what that is. According to the data sheet then, this is a NPN transistor. I have no idea why it's stuck to the side of this transformer. And it looks like, if we just go on the meter, the base is at this end. We should have a diode junction here. Yeah, move away, you can see it, there you go. Diode junction here, and we have a diode junction here. Yeah, and it's not short or anything like that. So it looks like a good transistor. I have no idea why it's stuck up there. Basically then, for this one, I need to order a MOSFET. I've had a look on AliExpress. I can get a pack of 10 for a couple of euros. I'm interested in repairing this, and that's because it's such an interesting design with no chip. Yeah, no control chip. The other thing worth testing is just check these diodes just to make sure they all read. Okay, is that one reading? Something might have a bad diode there. No, it's reading okay. Yeah, it reads. Get into it. Yeah, it reads okay. Reads okay. Reads okay. There's one more down here if we can get onto it. Get under this one if I can get under it. Yeah, I think I had it there. Reads okay.
And there's one more here. Again, if we can just get onto it. Yeah, it reads okay. So all the semiconductors read okay. There's no short on the output. My guess is this died because I've forgotten to solder one of these properly, basically. These transistors this side, there's none of them short. I think they're actually MOSFETs. So let's put that one on one side and let's look at the other simple ones. Try to keep this video something at a reasonable length of time, yeah? This is another one of the fairly basic designs. We have a similar setup, if you like. So what can we see? This is your bridge rectifier. There's 4 diodes. There's a few capacitors in here. This is your control chip. This is almost certainly the capacitor that's part of the startup circuit, the one where we have a high value resistance charging the capacitor to start this chip running. We looked at that on that diagram. This is the fuse. This is a quite large capacitor. One of these will be the high voltage capacitors. Let's see if we can see which is which. Can we read? So this is a 400 volt capacitor, and I'll just get the focus a little bit better. There you go. So this is 6.8 microfarad, I think it says. 400 volt. What's this one? It's on the high voltage side of the circuit. Can't really read the value very easily. It's just, it's probably down this side. It's just the way it's mounted, you can't read the value of it easily. This is your transformer. This is the output side, so we have the rectifier diode, we have a capacitor, which looks like it might be slightly bulged, that one, like that first one. This might be a bad capacitor. We have a filter, so this looks very much like the first circuit that we drew out. I think what we'll do with this one is we'll just check the short circuits first. So we'll get the test meter where we can see it. Let's go to normal continuity mode. And let's see if there's any short on the output of it. So we'll go there. Oops, I'll try and get it where you can see it. We'll go to here and we'll just go. Okay, so there's no short on the output. The meter's working. There's no short on the output. We can test the fuses. It looks like one of these I think is a fuse, and the other I think is a resistor. This one looks like a fuse down at the bottom, yeah. Looks like a fuse. And that reads okay. So, again, we have AC coming in. This is effectively a capacitor as a filter. This is a fuse. This is a resistor by the looks of it. Maybe an inrush resistor like the other one had. We can have a look. Yeah. This resistor, which is connected here, is basically feeding into the bridge rectifier. So this will be a low value resistor to prevent an inrush of current. And it reads, yeah, quite low value. Bridge rectifier, output of the bridge rectifier. This is the 2 negative ends. This is the 2 positive ends. And we can just look to see if there's any short. There's no short there. This one has just the one controller IC. I can see the port number on it as well. It has another little. Oh yeah, this I bet this is not a transformer. This is a little choke, a little coil. Let's have a look. Let's have a look. We can see bridge rectifier comes through the coil here and through here. This is like the inductor on the other one, which is broken off. Yeah. So that's what this is. This is double winded bobbin. It's just a filter to stop noise going back down to the mains. So this will have one large smoothing capacitor here and another one here. These will both be 400 volt capacitors. You can see they wired across the bridge rectifier. Yeah.
So these two capacitors are effectively in parallel, but via that. This is like the first diagram I drew, actually. And that's about it. Let's remove this slightly bulged looking capacitor. It's not particularly bad. And let's see if that is actually the problem with this one. So to remove this, this is the positive end. You can see the negative end in there. Let's get the soldering iron and let's see if we can get it off the board. Otherwise I may have to add a little bit of leaded solder. Yep, need a bit of leaded solder. A bit of leaded solder always helps to desolder things. See if I can actually bring the capacitor out this way a little bit. Yeah, I think it went, and then I'm going to hit this leg and push it the other way. Yeah, and it's coming a bit loose. And we just repeat this process a few times. Okay. One end is out, other end is out. So we have the capacitor. This is a 1000 microfarad 16 volt capacitor, and the first thing I want to know is the ESR bad, is the capacitance bad, like that first one we looked at. Straighten it up. So let's get the ESR meter. Let's have a look. Here's the ESR meter. Here's our capacitor. So just switch on. Okay. And what do we have? What's quite high, 4.5. That's a bad capacitor. Let's have a look at this one and see if we would detect this by using the capacitance meter. Okay, we have the capacitance meter. Range 2000, it's a 1000. Just untangle the wires slightly. How's this reading? How's it looking? Yeah, it reads about 500, so it's reading about half its value. So this capacitor is bad. I thought it looked a little bit bulged, but that's a bad capacitor. So let's replace this and see if this one works. Okay, so there's the replacement capacitor fitted. We'll just put this back together for the moment. There we go. I can put a little bit of tape around that for now. And then we can see whether this one is actually functioning. I'll remember to put the camera onto the light bulb this time. So the light bulb's under here. We set to current limit. So the power supply is now connected in series with that light bulb. This is the connector. And we just need the voltmeter to have a look to see if we have any output from this now. There we go. So we're on. We can connect the meter and then we'll switch the power supply on. So there's our test meter. Doesn't want to stay in. Let's switch it on first. So we'll watch the light bulb. Well, nothing happened at the light bulb. And this one's working, yeah. It's giving about 13.9 volts. I'm not surprised under load it's a little bit high. That's quite common for these 12 volt supplies. I'm assuming this is a 12 volt. We can just check. So, yes, 12 volt 1 amp. They don't often regulate very well without a load, so I'm not too worried about that. So we can say I think this one's working actually. I suppose we could just put a little bit of a load on just to be sure, but I'm pretty confident that is the case. Let me just put a bit of a load on it anyway, because I know you guys are going to say, Rich, why didn't you put a load on? If I don't, yeah. I know you guys are going to say that. The usual 22 ohm resistor. How much current's this going to draw? Well, let's just work it out, shall we? This is about a 2 watt resistor. So what does Ohm's law tell us? Well, first of all, what's the current? Yeah, so current, I current equals V over R. So 12 divided by 22. That's the current, 0.54, 0.55 amps, yeah. Wattage equals current times volts. Yeah. That's quite a lot of wattage, that is. That's too much for this. On top of that, I mean, this would supply 12 watts of power, but that resistor is going to get like well hot, so we need to find something a bit bigger than that. Let's see what we have. These are a couple of 20 ohm resistors effectively wired up in series, or I can just use one of them there to be 20 ohms, or I can use it as a 40 ohm, or I can use them in parallel as a 10 ohm. Yeah, that's what we can do with it. So let's try see what this 20 ohm resistor would do on our power supply. So here then we have, what's the current? I equals V over R. 12 divided by 20. 0.6 of an amp. Yeah? 0.6 of an amp. Times 12. This is watts, yeah? 7 watts. These should handle that. These are 15 watt resistors, yeah? So let's just use one of these and try and load our power supply with it. I think the best way to do this is with a couple of crocodile clip leads. I've connected a couple of crocodile clip leads, so from the black and the orange, which is this resistor, is now across the output of the power supply. I'm just poking the meter lead into there. So we'll just connect the ground lead and we'll switch this on and we can see what we get. So we have now 11.93, so that's regulating quite nicely. This isn't getting hot. It will gradually warm up. Yeah, it's warming up a little bit now. So we can see that just putting a load on that power supply is giving the correct output voltage. This is the fourth of these power supplies and the last one for this video. This being all you need to know about switch mode power packs part 1. The video is getting quite long, and I know you guys probably want to go to sleep, some of you, if you're not already fell asleep. Yeah. So we have a look at the fourth one. Again, it's a very basic design, and I hope you can see straight away what's wrong with this one. Once more, the output capacitor has bulged, it's failed. So this is definitely forming a pattern here that we've seen now in 3 out of 4 of these power supplies. Other than that, it's a very simple design. We have the bridge rectifier made up of 4 diodes. This resistor, brown, black, black, is a 10 ohm resistor. And if you look, this is the mains coming in, one side of it, and it goes through the resistor to the bridge rectifier, and the other side of the mains goes to the bridge rectifier. So this is just to limit inrush current, basically. It's to stop a sudden surge of current blowing the fuse when you first switch on because the capacitors have discharged. This looks like a low value resistor, red, gold, 2.2 ohms. That may be some sort of current sensing resistor without looking exactly where it's connected, but I think it is because one end is connecting to one side of the bridge rectifier and the other end of it is connected into the circuit where the controller IC is. So this doesn't have a separate MOSFET, it's built into this chip. We have a couple of diodes here and a capacitor. This is that small capacitor we talked about earlier, the one that charges up to get this chip running. This is probably the diode that feeds from another secondary on here. This diode is probably the one across the primary to take away the back EMF when the switch is off. And this is almost certainly an inductor. It's marked, well, if it's a valid resistor code, it's brown, green, red. It might be black, green, red, which isn't a valid code. But if it was brown, green, red, that'd be 1 0 and 2 zeros, 1.5K. But I'm sure this will read much lower than that, and that's because it's an inductor. So let's have a quick look. We can just go across this. Get to the other end of it. Yeah, 9.6. So I'm fairly sure this is an inductor. After the bridge rectifier, we have connected directly across the bridge here a capacitor, which is 400 volt 4.7, and then from this capacitor we go through the inductor, and here we have the other capacitor, which is another 400 volt 6.8. So we have here basically the same circuit we drew here with two capacitors in parallel, but there's an inductor in between them there. So first smoothing capacitor, inductor, second smoothing capacitor. This is a good way to get a very smooth DC and prevent noise going back that way into the mains. So that's what this one has. Because of that inductor, it looks like it doesn't have any inductors on the actual mains input. So this is the gap, high voltage to low voltage side, and on this side we're going to have output capacitor, which is clearly failed, output diode to rectify the output from here, and I would say under this is another inductor and then another capacitor. So on the output we have again the same sort of setup we drew here: diode, capacitor to ground, inductor, another capacitor to ground, V out. So it's this again. This is forming a pattern now. I'm sure you must be feeling quite confident about repairing these things. So once again, let's remove this capacitor and then let's see if it works with a replacement. Okay, there's the capacitor removed. The reason, by the way, I'm not worrying about voltage in the high voltage capacitors giving me a shock is because these power supplies have not been switched on since yesterday. They've had about 30 hours since they were last used, and that is more than enough to discharge capacitors of that size. Let's look at this one, because there's something fascinating about measuring the ESR of capacitors, I think, and I hope you also agree. So here we have the bad capacitor. It's a 16 volt 680 microfarad like the other ones were, and it's reading 37 ohms. Again, we'd expect the capacitance to read very, very low. Yeah, 100 microfarads rather than 680. So once again, both meters have told us that's bad. Let's change it. This one is not so easy to test in the original case because it had like little springy contacts which made a contact with here, and I've probably struggled to get it back together to do so. But another good thing with these sort of power supplies is they're great for little projects. If you're building your own projects, you need a 5 or a 12 volt supply and your little project's built into an enclosure, then you can use something like this internally, perfectly safe. So these little circuit boards, as well as the fact that you can put the power supplies back together, they really are ideal for your projects. We have here then an IEC connector, so this is how we're going to power this up. So I'm going to solder the two AC wires onto here, and then just plug an IEC lead in and we can test this power supply. To do that then we'll just get a bit of solder on this and probably just cut the wires a little bit shorter. Okay. Probably shouldn't do this over the circuit board because you're likely to drop blobs of solder where you don't want them, so slap my wrist for that one. Comments below. I've invited it now, haven't I? I've invited it now. Okay. Let's tag these AC wires onto this. Sorry, I'm out of view. First one. Second one. Okay. Oops, securely attached. There's no earth on my workshop anyway, and there's no earth connection in this anyway. I have isolation transformer, so my bench is completely isolated for safety reasons. I'll talk about isolation transformers in detail on another video actually. Okay. So we have that. Let me get a power lead and let's see what this one does now. Okay, we're ready to go. I've moved the camera over to the light bulb, but it probably won't even light up because this is such a low powered thing. I have the test meter connected, so let's switch it on and see what it does. nothing on the light bulb, and 5 volts. So that one is also working. So we have 3 out of 4 there, all with the same problem actually. That, guys, is the end of part 1. This video is plenty long enough already, but there will be a part 2 later this week, so you won't have to wait very long. In part 2, we'll have a look at these other 4 power supplies and have a bonus one for you as well. So these appear to have a bit more circuitry involved with them. They're also a bit higher power. This is a 2 amp supply. This one is a 4 amp supply, both 12 volt. This one, as you can see in here, just take this off. This is a 2 amp supply. And then finally we have this one. This is a 3.5 12 volt, 3.5 amp supply. So we can have a look at these 4 and see how they differ, if in any way, from the ones we've just looked at. And as a bonus, we're going to have a look at this one as well. So this has the output cable desoldered. I think I probably used the cable for some reason. This one is actually a dual supply, so it's 12 volts at 2 amp and it's 5 volts at 2 amp. Again, this can be quite handy for some sort of project, to be honest, if you were working on it. So as a bonus, we'll look at that one again. We'll see how it differs from the single voltage output supplies. In the second part as well, we'll also have a look in detail at the feedback system with these. These ones I can see have the TL431 and the Opto-Isolator, and that's probably the same on this one as well. The 2 are usually mounted very close together. I can only see the Opto on this one, and this one, yeah, this has two Opto-Isolators, so we can look at that circuit in more detail. But what I'd like to do, and I'm going to do, is I'm going to show you how to test the feedback circuit to see if that is functioning. This is very useful when you have an unstable power supply or one that's giving the incorrect output voltage. I think maybe one of these was actually doing that, I'm not sure now. But even if they're working, we'll have a good look at this. I'm going to show you in detail on the next video how the feedback circuit works and how we can test whether it's working correctly or not. So I hope you've enjoyed part 1 of this video, all you need to know about switch mode power packs to fix stuff, and I look forward to seeing you all very soon on part 2. Ciao for now, guys.